First of all, thank you for showing up to our talk, Leveraging the Power of Kubernetes with Patterns. Now, in the initial announcement, it said for fun and profit, but, well, that's only to get you to show up. Who are we? Well, my name is Wian Vos. I'm a solution sales professional, actually, at Red Hat. So usually I talk about OpenShift and stuff, but as this is JFall, we're not allowed. So we're going to talk about Kubernetes.
My name is Roel Hodzelmans. I work at Red Hat. No, just get it over with, right? Anyway.
You mean the IBM thing?
Yeah.
Let's not talk about that.
Yeah, let's not talk about it now. And I work on anything Red Hat related, that is OpenShift or the JBoss portfolio. That's me.
All right, so our talk today is based off of the work of one of our esteemed colleagues, Roel Hodzelmans and Bilgeon Ibrahim. It comes from a book, Kubernetes Patterns. You can buy it online. It's not very expensive. It's about $8 once it's finished. It's not finished yet, so it's 80% complete. So is our presentation. So bear with us.
Nah, just joking.
So, the steps between you and free food, because we do realize we're right in front of lunch, so I imagine you're all hungry. First, we're going to explain a little thing about design patterns. Then we're going to take you through the basics of Kubernetes. And I promise I will be short, about a minute 12. And then we're going to talk about some common Kubernetes patterns. Now, I don't know why the presenter thing is still showing up, but hey, who cares?
Never mind.
All right, your turn.
Fine. So, design patterns. Just a short recap of what they are, right? And where they come from. And the most simple explanation is they're nothing more than a simple way of describing a complex problem real fast, right? It's not something new. We've been doing this for ages. We've got a long tradition, even outside the software world, but in the software world, you see some of the most common ones up there with the Gang of Four, the design patterns, and the enterprise integration patterns by Hopke and Wolf. Actually, if you look at it, it's not really unique, but it is a way you can quickly communicate what you're thinking and where you need to look for your solutions. And they're basically everywhere. So this is one of the most simplest examples. Any car nuts here? I am. So V8, I like V8, Dutch government doesn't, they win, unfortunately. But city planning, we have the workspace boxes. We've got master-slave in your setup of your infrastructure. You've got the DAO. Everybody still remembers and hates these. Content-based routing, it's all over. And I could go on and on and on and on. But in essence, this is what we're talking about. A pattern is nothing more than a simple way to describe a repeatable pattern or a repeatable solution for an engineering problem. It's that simple. And the one thing is, it also can help you get the advice you need, right? If you're thinking about, I have a Java class and I need to build multiple instances of it, maybe looking at a factory might make sense. And this is what we're trying to achieve here today, give you those patterns in context of Kubernetes. And we'll do that in a structured way that's easy to follow. We'll do a problem description of what am I trying to achieve. We'll do a name of the pattern as it's identified by the Kubernetes community. And then, obviously, how do you solve it and why should you use it? I see people making pictures. Don't worry, I've already uploaded the slides to SlideShare. On the end, there's a QR code and a bit link, so you can easily download them when you need to. All yours.
If you still want to. So, Kubernetes introduction. K8S stands for Kubernetes, because Kubernetes is just too long a word. Don't know why. Who here uses Kubernetes on a day-to-day basis? All right. Cool. Who has experimented with Kubernetes? Who can give me a description of what Kubernetes is?
You're all shy.
Who here has a lazy arm? All right. So, Kubernetes, in short, because I can talk about Kubernetes for hours and hours, which I'm not going to do today because I only have 50 minutes and I have 75 slides to get to. So, Kubernetes, in basis, is a container workload scheduling system, or a kernel for your data center, or a platform, whichever you want to call it. It consists of pods. Now, pods are the smallest schedulable unit in Kubernetes. I'm going to talk about them a little bit later as well. Pods hold containers. So you can have a bunch of containers in a pod, and a pod will be scheduled on a node. Services keep track of where which pod is actually scheduled and make sure that network traffic coming into the cluster will find the right pod. That's all managed by the master. The master uses an etcd key value store to store its information. That can all run on physical, virtual, private, public, and hybrid cloud environments. And oh yeah, it can also manage your persistent storage. That is, in short, what Kubernetes is, does, and will do for you. Any questions? Save them until later. So, what about Kubernetes patterns? We have a bunch of categories that we use to classify those patterns. Now, I'm going to take you through the foundational patterns. And the first one is, of course, how do we create and manage an application in Kubernetes? All right, so we have three basic types of automatable units. There are more. We're just going to talk about the three simplest ones here. The first one is a pod. Now, a pod is a collection of containers. Why do we call it a pod? Because a group of whales is called a pod. And the whole container thing is full of whale references. Now, the funny thing about a pod is that it shares a network namespace. So if you have multiple containers, which everyone will advise you against because it keeps stuff less flexible. If you have a group of containers, these containers can reach each other on localhost. Simple as that. A simple deployment looks like this. So this is the deployment YAML for containers. We made it a habit to include YAML files for all the patterns we actually are going to discuss with you guys. I'm not going to go into them in detail, but they're in the presentation. If you want to experiment with them, go to SlideShare after this presentation. You can freely
Use all of them.
Use all of them. Next automatable unit is a service. Already touched upon it earlier on. So a service is a table construct that keeps track of the actual physical IP addresses of the nodes where certain pods are scheduled. So when you deploy a service, in fact, you say, all right, Kubernetes, I want you to keep track of this group of pods that make up my application so that actual incoming traffic for your application will get routed to the exact node it needs to go. This is a pretty important construct in Kubernetes because it's part of the Kubernetes magic. This actually works because of the Berkeley packet filter. So a pod will get its own IP address, but this is an IP address that's not on any physical or virtual Ethernet adapter. And the way that works is once a node sees traffic for a specific pod IP address come in, it will look in its table and see where the actual node is scheduled. And the way you actually deploy that, using that YAML, it's all pretty simple. Now, a deployment is one of the foundational constructs that actually takes care of scaling your application. Because a pod is just a pod. You can deploy a pod, but it's just there, doesn't do much. Now, in a deployment, you can say, all right, I want to have this pod, and I want to have 3 of them scaled over the entire cluster. and I wanted to use a certain type of node or a certain amount of CPU, a certain amount of memory, minimal number of pods, maximum number of pods. So a deployment keeps track of all the pods in your application. Basically like this, with the nice primary colors. And a deployment looks like this. So stuff to keep track of. You actually have your kind deployment here, some metadata. Kubernetes, full of metadata. It's awesome. You can metadata everything up to your elbows. So here it says, all right, I want to have 3 replicas of this template. And here you say, all right, which container? All right, Nginx certain version, and I want it to run on container port 80. It's all pretty straightforward. Again, after our presentation, please go home, try this out. It's pretty awesome. Works on any Kubernetes cluster. All right, so once you have an application, part of the magic of Kubernetes is you can actually deploy all kinds of upgrade patterns, which come standard with Kubernetes. So it's not only running your application, scaling your application, but it's also managing your application. That becomes a whole lot easier once you deploy a Kubernetes system. Now, oh, I see we have an old slide. Right, so I basically have 3 patterns. Please ignore the last one. We have 3. We have the create deployment, we have the rolling update, and we have a blue-green deployment that comes standard with Kubernetes. The first one is, well, how do I upgrade an application with 0 capacity overhead? So I have my old version. I need to go to a new version. How do I do that? With a cluster that's basically limited in its capacity. So you're at capacity with running your application. You don't have any extra, so you need to update your application. Well, basically, you use a recreate deployment. And what a recreate deployment does is it kills all the pods that make up your application now, deploys new ones. It's pretty simple. But it doesn't have any rollback, well, not an easy rollback mechanism, and it does create downtime. And the way you do it is basically, first, this is your original deployment YAML. The second one, just update your version, deploy this over this, so you don't even have to say upgrade, just deploy, and it will automatically deploy. Next question is, how do I upgrade an application with 0 downtime? Well, for that, you want to use a rolling update. And what a rolling update does is also pretty simple. It kills one container of your old application, and then it spins up an application of the new version. And it does that until all the application pods are of the new version. These are basically the 2 YAML examples we use for that. Oh. All right. So the last one is a blue-green deployment. Anybody know what a blue-green deployment is? So basically, what happens with a blue-green deployment, you have your old application, you deploy the new one, and you switch the service. So why do you want to use that? Because it gives you 0 downtime, but you need double the application capacity. So if you have that capacity, this is a great way to update your application. If you don't, well, it's not going to work. And of course, there's easy rollback because you still have the old service deployed. So if the new one doesn't work, you can just switch back the Kubernetes service to the old deployment, and everything should still work. That's basically what it looks like. And here are the 2 YAMLs. So what to look for here? is the service deployment. So once you, this is the original deployment, then you deploy that YAML, and you update this service to say, all right, Nginx version 1.11, and the service will automatically switch to the new deployment. Now, once you've verified that everything works as you expected, you can basically just undeploy the old version. All right, you're up.
Yes, thank you. One other note about the services, the cool thing is that you can leverage those to do canary releases. So that's why the fourth was on there. Is say, for instance, I want to check if I get a higher conversion rate if I deploy version A or blue, and or if I get a green one. I worked at a bank once where we would notice that during the 6 days of the week, we had the best conversion rate with a green button. So people would get most bank accounts and stuff like that with a green button. And for some mystical, magical reason, on Saturdays, the red button had a higher conversion rate. So stuff like that is only testable if you're capable of having both versions in production and to see which traffic you direct to which one. And that's where the canary release capability of Kubernetes is bloody awesome. Then, next problem. So we need to determine how much resources we will consume. Let's be honest, you have a cloud environment, awesome. As long as your credit card solves all your billing problems, you could scale out until the end of time. Well, not really, but hey, at least in theory it should be working like this. But you also have on-premise clouds. And there you're limited about the amount of resources you have. And so we need to be able to make sure that we make the right decision on what are the requirements we put on our infrastructure, what do our applications need, what decisions can we make when we schedule a workload to run anywhere on our system. And obviously, last but certainly not least, is can we take the input of the top two and determine where our capacity is going? You know? So if you look at the most essential infrastructure components, and there's way more, but we selected these two, is you need to be able to handle state. Now, there's multiple ways to handle state in a Kubernetes cluster. It's, for instance, taking a elastic system like a cache or a Redis or something the like that is capable of scaling with you, with your traffic, and as long as there's instances up, you can handle state. The other option, and it's the one that I see most in my customers, is, hey, I want state, but I want to externalize it to a persistent volume. So, how do I do that? And there's another one is around communication. So say I have a non-DNS traffic that needs to access my system, or I want to expose my database as a service and I want to host it on Kubernetes. So normal Kubernetes ingress works based on DNS traffic, which is awesome as a proxy, but it won't work for binary traffic, for instance. So you need another option, and that's where host ports and node ports come in. And the simple example in this case for persistency is something that is a little bit of a handwork depending on which kind of system you have. For instance, NetApps has dynamic provisioning. Most of the cloud providers have dynamic provisioning. We obviously have dynamic provisioning. But in essence, you need to first tell Kubernetes there's persistency available. So the first YAML on the left is, hey, I need persistent volumes, or I create persistent volumes. They have a specific size, in this case 10 gigabyte, and where are they mounted on that location. This is just telling Kubernetes there's persistency available. It's not using it yet. This is what happens on the right. So a developer that needs persistency makes a persistent volume claim. Kubernetes then deterministically checks which of the persistent volumes that are created matches the requested persistent volume and will serve that. The downside is if you don't have a dynamic system that creates persistent volumes beforehand on demand, you'll get the situation, and I had that at a couple of customers, that they only, oh, crap.
Oh, nice.
Nice.
It's a new version of Java, everyone.
Yeah, apparently we need to update. Could you switch back to Chrome? Just click Chrome. Yeah, okay, cool. Anyway, sorry for that interruption. So if you have created only persistent volumes for 100 gigs and a developer requires 5 gigabytes persistent volume claim, Kubernetes will match one of the 100 gig ones. Yeah? So this is why it's important to get dynamic storage. For node ports, for fun and reference, I've put in the one on the left, which is a host port, which is actually the one I would highly advise you against, because it requires a 3.0 combi to be unique within your cluster. And that's actually, it uses the IP, the host IP, plus the port, plus the, plus this port, and the protocol, and those need to be unique to find your address within the system, which is necessary, for instance, if you do something like binary traffic on a Kubernetes cluster. But honestly, there are better solutions. And one of them is on the right. That's the node port. Is then what happens is that there is a specific port range above 30,000, which is reserved by default by Kubernetes. And you'll assign one of those ports to the system. And actually, every host on which your containers might run will get that reserved, that if there's a service running that has node port 30,036 in this case, traffic will get automatically redirected to the pod that serves this request. It's a really nice way of doing this, which is way more scalable than the one on the left. There's one other, and that's relatively new, is that you can define an IP on your ingress router, which is unique, and that any traffic that has that IP as a destination gets automatically routed to a particular service and then to your pod. That's the one I would recommend, but it is a pain in the rear to set up the first time, and it doesn't fit on slides. So unfortunately, you need to look at that up yourself. Then, when we have all these requirements and we have the nodes and we have our persistency solved, obviously we need to talk about SLAs. Because in the end, what a Kubernetes is as well is a site reliability tool. And we need to make sure that we can serve our requests. And that, because of that, Kubernetes defines a couple of resources. Obviously, CPU and memory, networking, and then we can play around with those. So we can talk about having the application restricted on the amount of resource requests it can make. But we also can make sure that they get at least a minimum. And then we can say, okay, this is fine and dandy for a pod, but on average, I say, let's say we've got 1,000 virtual machines, then the average density I see is about 40 containers per virtual machine-ish, right? Your mileage may vary on this one. But that would mean 40,000 containers. So or pods. If I have to manually make sure that there's settings for all 40,000 of them, I'll go bananas, right? You don't want to do that. So you also have the capability within Kubernetes to put that limit on a namespace level or a project level, depending on your terminology. And those resource quotas will immediately translate to my pods, and even I can do one step better and talk about all of my pods together. So how does it look like? It's actually really simple. On the left, you see an example that I put a limit on a pod, and I said, listen, you request, so that's your bare bone minimums, that's what you want to have, 200 megabytes of memory, you have 100 megabytes of memory, and you have 200 CPU cycles, and the limit is double that, or ish. You can read, I don't have to explain that one. If you look at the project limits, you get an additional control. You see here, you have a resource quota object within Kubernetes. And in that resource quota object, I have a specification that I have a hard limit on 2 pods in this, in every project, namespace that has this quota. No? Really simple, really straightforward. And in terms of CPU and memory, we've got the limit ranges is that there's a max and a minimum limit for all containers that have, exist in the project that has these limits. So even though I declare a pod or a container to have more resources, Kubernetes won't schedule it because I won't make the limits. Yeah, it's as simple as that.
Yeah, one remark.
Yeah.
We are Red Hat, we have OpenShift, and in OpenShift, we call stuff a project. Now in Kubernetes, whenever you see project, it's actually a namespace.
Yeah. Sorry, I normally do OpenShift, so.
Yeah.
Then obviously we need to talk about quality of service, right? So you need to talk about, okay, how does Kubernetes make sure that you get the resource, right? How do we prevent a noisy neighbor to take all of our resources? And obviously limits are one option, but then how does the ordering work? And it's actually quite simple. If you look at the top, that's the quality of service that says you'll get resources as you demand them. There's no limit set, but that also means that you're last in row, right? The guaranteed pods go first. So the lowest one is actually the most strict. It says I have a minimum requirement that is equal to my upper requirement, so it'll take the resources all the time. But that's the first one. That's the first one that gets the resources. Yeah. So there's a trade-off you can make. You can, for instance, we have an OpenShift Online environment which is open to all, which where we say we overcommit. Guaranteed pods cannot be overcommitted. Yeah. So this is where you can make the trade-off. Will my workload be at peak load all the time? Probably not. So if it's not, then maybe overcommitting makes sense. Yeah? Structural patterns. So the next section is a little bit more deep therein. This is actually, Wian just said that you don't put 2 containers into a pod. This is the exception to the rule. And I have to be honest, with great power comes great responsibility, depending on whether you're really looking into it. It did not come from Spider-Man, FYI. But this is a pattern. Say I have a container. I like the container. It does a lot of things for me, but I need to extend that functionality. Now, the normal way to do that is to change that container and update it with the new spec, build a new version of it. But that isn't always possible, and from a separation of concerns perspective, might not be a good idea. So that's where we leverage the ability to have multiple containers into a pod. And in this case, the name to do so is a sidecar. That's the name of the pattern. And again, it's about enhancing the capabilities of the original pod. A simple example is, in this case, and please don't do this in production, it's just a sample. We have a node container, and that node container is static, right? And it takes the actual files that it needs to serve from the file system. Remember that Wian told you that if you have a pod and you put multiple containers in that pod, they share everything. They're on a local host. They can reach each other on local host. They share persistency, they share networking, they share ports. So in this case, from a local host, you can read to the disk from the disk from the node container and have a separate container that is pulling Git and writes any changes to your disk. So in this way, we have an automatically updated node container every time we do a commit, which is pretty darn awesome if you're developing in Node and you don't want to redeploy every single time that you do a change. Yeah? It's a really simple, powerful example, but please don't do this in production. Yeah? I have better examples of what to do in production. This is another example. You see here, it's a little bit long, hence the arrow. I split it up in two halves. It's a pod, and this pod has an application container in it. It's based on Alpine. I wanted to show that I'm not just Red Hat, especially since we're IBM now. Or just joke. Share a volume mind in var log, and there's a sidecar container in Nginx that takes that logging and shares that outside on port 80. It's a real simple use case of that other people can access the logging without changing the original container or opening any further pods, any further configuration in that particular container. Really simple, really powerful, really straightforward. And there's another use case where we use these things. And this is an initializer. So occasionally my pod needs to be pre-warned with maybe specific data, maybe there's specific permissions I need to set, maybe there's additional workloads that I need to run before I can run the pod that is actually or the container that is actually serving my request. So in this case, I can use an initializer pod. And if you look at the relatively simple example is, hey, one of the containers in my pod is doing some pre-work and it gets checked off. And if you have multiple, it'll work them down in sequence. And then my actual container, application container, is booted. It's awesome, but keep in mind that pods are the smallest unit of orchestration within Kubernetes. So remember that I just said we have quality of service and we've got resource requirements. If you have a really hefty initializer container that preloads stuff or sets permissions based on separation of concern, you put that in an additional container, Kubernetes will see that as one deployable unit. So even though it might be some spike that runs only 2 minutes to boot up your system, it'll take the spike and add that to the requirements of your pod. Yeah? So there's downsides to this. That's why we say use this with caution and use this responsibly. You could go a little bit further, but in the interest of time, I'll skip this. Read the book, right? It's $8, please. How to decouple a container's access to the outside world. This is another specialization of a sidecar container. Instead of taking a normal sidecar container, you add an ambassador or a proxy container or sidecar. And this will proxy the connection to the local world. Most of the time, this is used for circuit breaking, tracing, access control list, and the like. Who knows the best known example for this? Thank you, Istio. That's the service mesh, the envoy, proxy, sidecar, ambassador container. That's a lot of words, but in the end, it's a proxy. Simple example, and I didn't use Istio because, hey, you'll be hearing about Istio a hell of a lot today, is here we've got a Python container via localhost talks to memcache, and that behind that memcache filter that's being sharded done and caching done, I don't give a monkeys when I'm the Python container. I just want to speak to my memcache service. Yeah? So it's a simple way of abstracting away implementation logic that does HA or load balancing or circuit breaking of services. And also the other way around is also possible. So how do I decouple the container from the outside world? It's an adapter. Again, this is not rocket science. This is what we're doing in case of monitoring and logging, for instance. So again, the simple example, we have a container. It's a simple Java container where requests come in. It'll write stuff to the disk, for instance, logging. And then we say, okay, but we want access to this logging. Can we please make a simple adapter that reads from that logging and exposes that to the outside world? I see this a lot with agent tools. And please, if you have your security department, have them talk to us. Agents are not necessary in the new world anymore. But if you still have them, this is a way to make sure that it will run and that it will scale as you intended it to do. Configurational patterns, all yours again.
Thank you. So, who's still not asleep? Wow, look at those arms. More than actually people using Kubernetes in production. That's good. So, configurational patterns. We're going to take a step back. These are not as complicated as some of the structural patterns we've seen. So, yeah, and I know, I'm in a hurry. 10 minutes. So, the basics. How can apps be configured for different environments? And we have a bunch of solutions here. These are not all solutions available in Kubernetes, because Kubernetes is open source, so we have 20,000 ways of doing exactly the same thing. 3 main patterns. We have EnvVars, environment variables, we have EnvVar secrets, and we have configuration maps. These are pretty much the bare bones basics. So in EnvVar, it's the simplest way of injecting a variable in a container while being not secure and very non-dynamic. Kind of looks like this. So basically, here you say, all right, environment name. So this is going to be the name of your environment variable. This is going to be the value. Biggest problem with this, if you want to use this to do OT, AMP, you're going to have to come up with a different YAML for every environment if you want to change these. It's not very flexible. And this is readable to everyone who uses the YAML. So it's also not very secure. I wouldn't recommend using usernames and passwords like this. You can if you want to live dangerously, but yeah. So how can I configure an application using a secure method? And for that, Kubernetes has secrets. And yes, you can use secrets as an environment variable. The way that works, you define a secret, and these are very securely based, 64 encoded. And here you can say, all right, I'm going to take it from this secret. The name is my secret. The key is username. So this is going to be the name of the environment variable, and it's going to get the secret from my secret and the key username. So this variable is going to translate to that. Plain and simple. How can I configure an app using more complex configuration? Because environment variables, although they often do the trick, it's usually not enough to do your entire configuration, right? So configuration maps are also a pattern commonly used in Kubernetes. It's facilitated by Kubernetes. It's secure. It's decoupled. It's a means of decoupling your configuration from your pod specification, which is also good. So you can use one pod spec to do your entire OTA and P while switching out configurations. That's pretty cool.
And it's a hell of a lot better than the property files of old, right?
It's kind of a property.
Or for now, maybe.
It's kind of a property
I don't know.
file. Yeah. Just don't tell them that. All right, so 3 main types. You have a config map from a value, which you specify like this, just metadata. A config map from a file. This is the command you can actually use to compose this. Pretty handy. And a config map from a directory, because why stop at file, right? Now, the way to consume this is basically, you have your pod spec. You can also do this in a deployment, of course. Make it a little more functional. And you mount the config map as a volume, which then becomes available in your container. All right, the last one, and I think the most exciting one, especially as we're here at a developer conference. A little question. Who here is actually a developer? Wow.
Who actually writes Go? Oh, damn.
Oh, crap.
There's a little to do in here.
All right, who would like to write Go?
Oh.
There's a little more there. All right, this is a great way to get started. Well, maybe not, but yeah. Advanced patterns. So, how do I package, deploy, and manage an application natively on Kubernetes? So how can I get Kubernetes to specifically manage my application as being part of its own system? Well, you use an operator. Anybody heard about Kubernetes operators?
Quick show of hands. Too few. Look
All
them
right.
up.
Anybody ever written one? No. No? Yes? No? All right, so what does this do? Kubernetes operators give you a way to extend the Kubernetes API without changing the source code. You can actually add your own logic because Kubernetes works on a loop, a control loop, right? You declare a certain state for the cluster, and the control loop will make sure that the state conforms to what you actually want it to do. So to make sure it coheres to the declaration. Now, by adding an operator, you can actually add your own types to that state check and have Kubernetes execute the logic you want for that actual type. So what does that look like and what does that do? All right, so this is basically how you deploy an operator. Now, this is not how you write an operator. If you want to know how to write an operator, look for Kubernetes operator SDK, which is a software development kit that Red Hat actually put out there for everybody free to use. But some funny stuff you can actually then do once you have that operator in the ecosystem is, all right, API version. Hey, that's different. All of a sudden it says etcd. So this is when you deploy the etcd operator. You can use this part of the Kubernetes API, which has magically appeared because the operator is there. And you can deploy something of the kind etcd cluster. Okay, all right. So basically, just like deploying a pod or a deployment or a service, you can say, all right, I want to have an etcd cluster, size 3. Now, what that size is, that's defined by the logic behind it. So that could be 3 pods, if you decide to do so, but it can also be 6 pods if you say, all right, size 1 is 2 pods.
That's actually a good point. So one of the operators that exists, is, for instance, is a Kafka operator. So who's using Kafka right here? See, a little bit more than no go. So if you look at Kafka, you need not just the Kafka clients and pods and everything. You'd also need, for instance, the Zookeeper to manage and to handle state. So what the good thing is that the operator for Kafka makes sure that the consumers of your Kafka operator just have to tell the operator, just give me 3 instances of Kafka, and the rest is up to you, dear Kubernetes. And if you want to do an upgrade of that Kafka cluster, you just tell the operator, upgrade, make it so. It's the best way to feel like Picard.
If you want to have a great example of that, look at the Streams project. Streams.io, I believe.
Streamzy, yeah.
Yeah, Streamzy.
It's the upstream of it.
It's pretty cool. It actually makes Kafka integral to your Kubernetes cluster. But, so, getting back, because the lady has warned us we only have 5 minutes left, the size of your cluster is going to be 3, and the version is going to be 3.2.13. Now, if you specify this, and you've written the logic for that Kubernetes can use to actually check those parameters, and you can add many, many more here, because that's all up to you, Kubernetes, in its control loop, will make sure that that cluster is there, and that it's of that version. Now, if you specify a different version, and your logic is able to handle that, it will upgrade to a different version. But you can make it do more. The etcd operator also provides a backup functionality. So by actually using this operator, I am now able to tell Kubernetes, all right, I want you to take this specific etcd cluster and take its persistent storage and back it up to S3, for instance. And then all of a sudden, is becoming pretty powerful. Because right now you have to actually, every time you want to do an update, you have to run one of these. But in future versions of Kubernetes, this can be scheduled. So all of a sudden, Kubernetes can take care of all kinds of repeatable jobs for you. Now imagine if you're writing an application that's horizontally scalable, you can also say, all right, at every control loop, I want to have some metric checked, and depending on that metric, I want to have my application scaled. Stuff like that. So it's pretty powerful way to extend native Kubernetes without actually changing Kubernetes. All right, that's it for us. Any questions?
Yeah.
Yes.
I think you can also make cron jobs in Kubernetes. What is the advantage of integrating it into Kubernetes instead of keeping it separate?
Well, yes, you can make cron jobs, but that functionality is still pretty much under development or in flux, as we say. So that functionality might go away, it might be extended.
Plus, let's be honest, right? You can use the Kubernetes job scheduler to have the situation run, but what happens in that job is still something you programmed out, right? This is a simple way to write an operator that does that for you, and you can leverage that on any Kubernetes distribution, right? It's not just Red Hat specific. You can run this on AKS or one of the others as well. And the good thing is, especially, I don't know if any of you are from an independent software vendor, as we call it, somebody that builds a solution with software for somebody else. If you build something like this and you give your customers an operator, they also have the capability, to, if you write your operator smart enough, to do the upgrades themselves, to have the new version deploy, to have the scaling issue solved. All those tasks that you normally either need to leverage other native capabilities of Kubernetes for, or have to manually do that, or maybe use an Ansible playbook or a Helm chart or something the like to do. That's what the operator does for you. It's basically making the pure play manual typey or clicky admin obsolete. And let's be honest, if you look at the red tape we're dealing with in the development world, we want that guy gone.
Oh yeah, we're talking to developers, so we could say that now, actually. That's pretty cool. Yeah, so disclaimer, all of this works on Kubernetes. Yes, we are Red Hat. Yes, we have OpenShift. Please look that up. But all of this plain Kubernetes.
Yes. And then last slide for the QR code. So the QR code is on the top. There's a small link as well. Please don't forget to rate us high, obviously.
Yeah.
And thank you for your time. And one last remark, this is the shortcut to the food.